Okay, we're going to finish our discussion on zeros, but let's just kind of recap where we are. What we saw in the last lecture is we can write a differential equation as a transfer function, and when we go to look at that transfer function, we have poles and zeros. Zeros are the roots of the numerator polynomial, and the poles are the roots of the denominator characteristic polynomial. All right. Uh, so you have, and when we've analyzed these things to this point, we can look at a transfer function or a differential equation, and we can get static gain, we can get the poles, and the poles determine every pole gets a response. So, and for every pole, we have time constants, settling time, damping ratio, natural frequency, damp natural frequency. And so every pole gets a response. So the poles determine the dominant transient characteristics for our differential equation. All right. And so what we then saw is the zeros, what they do is they affect the amplitude of that response. And if our zeros are chosen well, and we have a stable pole, we can in fact cancel it. We can drive that amplitude down to basically zero. Okay. So we're going to take a look at this at a little deeper level now. So suppose I have a second order system, but it has two real poles. So if I'm analyzing this thing, first thing I'm going to do is I'm going to say, what's the static gain? Let the S's be 0. I got 16 over 16. Static gain is 1. That says for a unit step input, I apply a gain of 1 to 1, get 1. All right, so the final value will be 1. All right, then I analyze the poles. I'm going to get a response due to each of these, but if this one is the dominant one, S plus 2, this is the closest one to the imaginary axis, so it's the last one to die out. Time constant is a half, settling time is 2 seconds. This puppy, S equals minus 8, time constant 1/8, settling time 1/2. It's long gone as this thing keeps going for 2 seconds. Okay, so this is the dominant part of the response. We also see we have no complex roots here, therefore we don't expect to have any oscillation. So we understand that. Now suppose I have this, I take this system and I come in, all right, we apply the step input, we're gonna have almost the same system except I'm gonna put an S right in here in the top. From what we saw last time, we understand adding an S in here adds a derivative effect. And that is indeed what would happen. So let's just summarize all of that. Here's the second transfer function where I've now added an S up here. All right, same input, step input. Here is the response. It's simply the derivative of that. So look what we have. This is 16 over 6 e to the minus 2t minus e to the minus 8t. All right, and it would produce, subject to some artistic impressions, something that looks like this. Okay, so now what we see here is we have, oops, made a little stray mark. We've introduced this kind of bulge here. All right. Well, now let's suppose we looked at ks plus 16. So here is our original response, or original transfer function. Now I'm going to make a third one. That's a combination of this one and that one, except I'm changing the 16 to a k. So ks plus 16 over the same poles. I'm still applying a unit step input. All right. So what's going to happen? I can break this up into this response right here, the 16 over the poles. That's going to produce this. And ks over these poles is going to produce a multiple of that. As I adjust k, this peak is going to get smaller or bigger as I adjust that. Okay? So here we see the effect of adding in. We've now added in a 0. And where is that 0 located? We've now added a 0 at s equals minus 16 over k. And we can adjust k to be whatever we want. But this is going to cause this, what looks like an oscillation. It actually has a bit of a, it's going to go up, it'll come down, and then it will come up to this steady state value. So this can fool us. It kind of gives us a look of a little bit of a second order system. All right. But what we can see is by adding that 0, I can cause overshoot. All right. Damping hasn't changed in the poles, but because of that 0, I've added overshoot. All right. So here's what we can see is that zeros can add or take away oscillation. So that's another effect they can have. But let's take a look at that again just a little more deeply. And so here's this 0 we have added, minus 16 over k. Well, here's what I want you to take a notice of. As k gets bigger, okay, as k gets bigger, this peak will become more dramatic, up and then back down. But as k gets bigger, the 0 associated with this is becoming smaller, minus 16. If I made k 100, this is, less than, there'll be minus 1 is out here. It's moving towards the imaginary axis. As k gets bigger, it moves closer to the imaginary axis. And as it does that, this peak gets bigger. All right? So the effect of the 0 becomes stronger as it approaches the imaginary axis. All right, so here we have influence of the 0 becomes more pronounced as this thing moves in. So you're going to get more of this big jump. And now you may look at that and go, well, wait a second, that's not good. You can look at this and go, this is kind of concerning. We can suddenly have some nice docile machine that goes wham, hits somebody or something if it's a robot. And I'll give you another perspective. So back in the mid 80s, as I was doing my master's degree, a company well-known company that makes robots, was having problems with one of their robot designs, and they sent it to one of the professors at Purdue to look at the problem. And basically, what was happening is there was so much static friction in the robot that it was not starting, and it was making it very jumpy, and for some inputs, it wouldn't even respond. It would just stay locked, okay? And the problem was static friction, getting it going. And so what they did is they actually basically rewired the robot, and they set it up such that they put zeros into the numerator. And so, which would predict, in the linear world, it would predict this effect. But here's what happened. All of this jump represents energy. The system is trying to dissipate energy. And so what happened with the robot is all of this got absorbed to get it to quickly go past static friction and then, frankly, smoothly go where they wanted it to go. So they didn't actually get any of this. It's predicted, didn't happen. Now, the energy that's associated with this most definitely did happen, but it was being absorbed by the nonlinear static friction effects, and that got it going, and then it wound up looking more like you would have expected it to originally. These things can be used to beat friction. So if you have a system where you need to get some early energy into the response for whatever reason, this is how you do it. You can have the same system and rework stuff so that you get a 0 up top here, and now you'll have that extra energy really early to accomplish whatever the goal is that you have. So that's how you can use zeros. They are used in the real world. I've seen it happen. Anyway, we're going to leave this lecture at this point, and we're going to move on to another topic here. See you soon.